So we start our session with the invited talk by Professor Nathaniel Berg. So let me just first introduce Nathaniel before his talk. So Nathaniel is an associate professor at ELSI, the Earth Life Science Institute in Tokyo Institute of Technology. And his long-term research interest is understanding the living systems through mathematics and computer simulations using tools of information theory and statistical mechanics, as well as artificial life approaches. So, and recently his work is getting more on the understanding emergence or origin of agency or individuality in physical systems, and also in the eyes of Bayesian inference, Bayesian statistics. So I believe his talk today is also on this topic. So please, Nathaniel.
Thanks very much. Okay, so I will talk about Bayesian agents in a physical world. So this kind of doesn't get so much into the question of individuality or situatedness. So those are things that I think are kind of like big open questions in relation to this. So really glad that I'm here in this session. So a key question in artificial life is, what does it mean for a system to be an agent? That's kind of been like a core question of the field since the beginning, right? So we look into the world and we see things like human beings and animals that we really think of as having agency. They do things, they have goals that they try to achieve, they have knowledge about the world that they update when they get new information, right? And we see things like cups of water that don't really seem to have much in the way of agency. And so the particular version of that question that I'm addressing here is, what does it mean for a physical system to perform Bayesian reasoning? There's a much easier, much simpler question, right? We want to say, suppose I've got this thing, it could be a robot, it could be a human being. I want to say that this thing has a prior state of knowledge and it updates that to a posterior using Bayes' theorem. You may or may not believe that human beings do that. I'm not sure if I do. I mean, except when we do it on purpose, deliberately. But the question is, what does it mean to believe that? What does it mean to say that a system is or isn't doing that? And the answer that my colleagues and I, so this is, I don't know if I said at the beginning, this is joint work with Martin Beale, who's here, and Simon McGregor, who isn't. This is, we'll give an answer that is along the lines of Daniel Dennett's ideas. So Daniel Dennett, as I'm sure most of you know, is a philosopher of consciousness. And I won't go into great detail about what he says, because what we say isn't exactly the same, but it's somehow related. And what we're trying to do in many ways is to produce a kind of mathematical version of Dennett's ideas. We really want to take the sorts of things Dennett says and make them into concrete mathematical statements. So what we say that's inspired by Dennett is that whether a system performs reasoning or not is a matter of interpretation. So I can look at a human being, and I always have the option of taking what Dennett calls the physical stance, of saying that the thing in front of me is actually just a big collection of atoms held together by electromagnetic forces. Its behavior can in principle be explained purely by the laws of physics and talking about how those forces act. And in principle, that does, we believe, or I believe, can explain everything that we see. But it doesn't really get you very far practically in trying to understand another human being. It's much more efficient. Makes much more sense to treat another human being as an agent, right? So the agency thing is a kind of interpretation. It's not really part of the physical system at all. It's a story that you tell about it, but it's one that really helps you to understand the system. At the same time, I can try to tell the agency story about this cup of water. Maybe it's trying really hard to fall down, but then my hand is stopping it, so poor glass. But that doesn't really add anything compared to the story, the same thing said in terms of Newtonian mechanics. Unlike the human being, doesn't really help me very much if I make that interpretation. And so actually one of the things we'll end up saying at the very end of this talk is that for the particular notion of interpretation that I'm going to explain, usually some systems can't be interpreted at all. They're just physics. So this talk is a kind of a philosophical talk in a way, but it's philosophy backed up with maths. The work that we did builds on recent work in category theory, but you don't need category theory at all to understand the idea. So although I'll occasionally use notation from category theory, I will mostly be giving the intuition in this talk rather than going through the formal details. So the vast majority of the talk will be spent giving a new perspective on known results, trying to just sort of get the idea across of what we want to say. And then the last few minutes will be talking about the new work that we've done and the open questions that it raises. And I kind of hope like that this will really lead to some discussion. It seems quite like it touches on some of the key themes of the session, not others. And I really hope that some good discussion can be had. So, and the work that I'm going to talk about, if you're familiar with the free energy principle, which you guys mentioned in the intro, you'll definitely see parallels to this work as I go through the talk. So I don't know if I can do justice to the free energy principle very on one slide, but kind of the idea of the free energy principle is that in some sense, certain physical systems, ones that are supposed to be commonplace, do variational inference, which is a kind of approximate Bayesian inference, and that you can look at systems that have a so-called Markov blanket, and you can say, look at their stationary distribution and derive from that priors and posteriors and all sorts of things about how they are supposed to reason about the world. It's a really fascinating idea, and this work is very much inspired by, in particular, Simon McGregor has spent maybe a decade trying to understand this set of ideas. But when you really try to dig into the free energy principle, it rests on some really weird mathematical assumptions. And I think it first seems like this very broadly applicable thing, but then you kind of get into the details and you're like, wait, what, you're assuming that? So I think it's fair to say that the community, the FEP community, is really working on trying to understand which assumptions are needed. This work could be seen as an attempt to do something somewhat similar, but in a much simpler way that tries to avoid any of those difficult assumptions. So the kind of mystery that I want to point out to start with is that, say we've got an agent, it's in the world and it's doing Bayesian inference. Let's say, for the sake of argument, that this agent is a robot, so we don't have to worry about whether representations really exist in the brain or anything like that, right? It's a robot, it's in the world, it's being programmed to have a prior and updated to a posterior. Even in that case, there's a bit of a mystery about the situation, because there seem to be these two disjoint worlds. On the one hand, there's the inference world, where the things that live in the inference world are probability distributions. So in that world, there live priors and posteriors and mutual information, and Bayes' theorem is what determines how things update. And then we also have the physical world, in which the robot actually exists, right? The robot is a physical thing, it's made of atoms and transistors and so on. So the robot and the world together form a dynamical system. It can be divided into two coupled systems that interact. There are dynamical laws that say how this thing changes over time, but there's no probability distributions in that world. I mean, the laws that update it might be stochastic, but they don't. So there's probability distributions may be involved in describing it, but they don't update according to Bayes' theorem. It really is a different world that follows different rules. So the question is, how do those two worlds relate to each other? And what we want to say is that you can make sense of this by defining what we call an interpretation map. And the way that works is as follows. So you have this physical system started in the physical world. We're going to assume throughout the talk that time proceeds in discrete steps. We think that we can relax that assumption, but that's what we're going to assume throughout. So time goes in discrete steps. The system is in one state at one time, changes to another state at another time, changes to another state at another time. The reason it's changing states is because it's interacting with some other system, but that's not drawn in this diagram. Then at the same time, in the inference world, you have B here stands for belief, and generally I'll use priors and posteriors and beliefs somewhat interchangeably. I always mean a probability distribution over something. So you've got a belief over some set of variables that the agent has beliefs about, and that's changing over time too. And in the inference world, the story is that's changing over time because the agent is getting data and using Bayes' theorem to update its prior to a posterior, which then becomes a prior for the next step, and so on. the idea of the interpretation map is simply that it's just a function that maps the state of the system to probability distributions over these hidden variables. And the point is that there are two different stories that you can tell about why the beliefs are updating. There's the one I already told, which is that it's updating using Bayes' theorem. That corresponds to the orange arrows going along the top of the diagram. But there's another story, which is just that the physical state is changing over time. The beliefs are a function of the physical state. That's what the interpretation map is. And the beliefs are just changing over time. Just because the state's changing over time, the beliefs are a function of the state. So the beliefs are also changing for a physical reason. The point is that to be a good interpretation map, these two stories have to be consistent. So that's how we can kind of reconcile the existence of the mental world, if you will, the world of inference with the physical world. That there has to be this consistency between the physical story and the story of inference. And this turns out to be kind of a prosaic thing. This is in a sense not a new thing. It's in a sense been around since the very beginning of Bayesian probability. Now suppose, and the example to see that is the notion of a conjugate prior. So suppose that we design a system to perform Bayesian inference, a very everyday thing that you might do if you ever had the need to do so. So we're going to do inference based on the assumption that there is a hidden variable and that our system that we're coding up on our computer, our system is going to receive sensor inputs. So S for sensor input, H for hidden variable, is going to receive sensor inputs that are independent and identically distributed given the hidden variable, right? So we know how the sensor inputs depend on H, but we just don't know the value of H. So the way that we model that is we have this thing called a model, which is a conditional probability distribution of sensor inputs given the hidden variable. Somebody just gave that to us. We don't have to worry about where it came from. We just know that. And we have a prior over the hidden variable, our initial state of knowledge. We think maybe it's this, maybe it's that, we don't know. So that's represented with a probability distribution. And then when the system receives some data, we're going to update the prior to a posterior using Bayes' rule, which is, again, very straightforward thing. P of H given S is equal to P of H times P of S given H over P of S. Very straightforward thing. And if you were if you were lucky enough that your hidden variable was a discrete random variable, you might just implement this directly. You store P of H as a probability distribution. You store that as a vector, and then you just use this equation directly. And you might do that in the continuous case too by approximating the probability density function somehow, but you typically wouldn't do that because there's a much better way. Typically what you do instead would be to represent the priors and posteriors using a parameterized family of distributions, for example, normal distributions, right? So you've got your continuous hidden variable, your prior is going to be a Gaussian with some mean and some variance. And if you set this up, if you choose things correctly, you have the right model and the right prior, then it turns out that you can do Bayesian inference just by updating the parameters. So the point is your prior is a Gaussian, and if things are set up nicely, your posterior will also be a Gaussian, just with a different mean and variance. So there's an update function which updates, so this thing theta is often called the hyperparameters. In this example, theta is the mean and variance of a Gaussian. In general, I just call it theta. Actually, in general, I'll call it M later on. It's a bit, anyway, call it theta for now. If this is chosen correctly, then all you have to do when you get some new data is choose the right new values of theta. So the fact that this is possible is actually kind of weird and non-trivial. Like to me anyway, it's like, wow, it's kind of magic. It's a weird coincidence that if my prior was a Gaussian, my posterior was also a Gaussian. But there's like, it happens quite often, and it's understood why it happens. So you can go on Wikipedia and you can look at this big table of conjugate prior distributions. And the thing that I want to draw your attention to is the right-hand column with these equations in it. Those look sort of complicated, but they are just equations. They are just saying, if you get this data, this is how you should update the parameters of your beliefs to get your posterior beliefs. So when you implement this thing in code, all you're really implementing at these functions is one of these functions from this right-hand column. Like the computer, in the end, once you've written your code, The computer knows nothing about Gaussians or anything else. So all it does is it just updates the parameters of this distribution. And the idea is that that's kind of always what happens. So like what you always have is just the physical world. Like you have the computer has got some data stored in it somehow, and that's being updated somehow according to whatever program is in the computer. But it comes with this interpretation, or when the way you wrote it, it came with this interpretation that these things are not just arbitrary numbers, they represent the parameters of this distribution. So the distribution isn't in the computer, only the parameters are in the computer. And so this is what I'm referring to when I talk about interpretation maps, right? It's the thing that takes the parameters, which are really existing physical things, and turns them into a probability distribution, which isn't a really existing physical thing. It kind of exists in the space of interpretation. It's a story that you tell about the system. So the key kind of philosophical idea here is something that I've been calling the design perspective versus the natural science perspective. The idea is that when we're designing something, this notion of interpretation is so obvious that we never even think about it, right? We know what we want. We know what inference we want this thing to do. We started with the model. We started with the prior. We were just trying to implement that, and we were happy because we found an easy way to do that where we didn't have to worry about representing continuous functions in computer memory. And then we never really kind of implementing that, you never really worry about the fact that somehow the probability distribution has disappeared and doesn't really exist anymore. That doesn't really matter. But if we're merely observing something, if we're looking at a system, we've got a brain, we're trying to figure out if this brain is doing inference, then we don't have access to this right way of interpreting it. So we have to ask a much more complicated question, which is, does there exist an interpretation? Does there exist some problem that this thing could be seen as solving? And if so, is it unique? And the answer is no, it never is. So this is the point, right? It becomes like this slightly more subtle perspective on the same thing. So I'm going to go back through the story about conjugate priors a second time, but from the natural science perspective. We start with the machine that's doing the updating, and then ask the question of, does there exist an interpretation? And then we'll see a bit more clearly what this thing I'm calling interpretation really is. So this is the idea where you have a physical system that we're observing, and it's receiving inputs from some outside world. The question is, when can we interpret it as performing Bayesian inference? By the way, this specific case of inference that I'm talking about, where you have observed IID samples, is only a special case. We've worked out a more general case of Bayesian filtering, but it's just easier to talk about the special case, even though it's kind of less novel. So I'm only going to talk about a deterministic machine. So this machine is some deterministic function, gets inputs and changes its state deterministically. This does all work with a stochastic machine, but it just adds a bunch of subtleties that would take time to explain. So I'm just going to explain the simpler case. So we're going to use a bit of notation from category theory. I'm not really going to explain it because it wouldn't really be possible in a relatively short talk. But the point is, a machine is defined by this update function. And this notation, this graphical notation, just represents a function. It's a function that takes the initial state and a sensor value and returns the next state. That's all it is. Right, and we're given this. This is all we're given. This is all we know. We want to know whether this can be interpreted as doing Bayesian inference. In particular, we're not given any information about where the data comes from. But we do know what its next state would be for every possible input, right? So we have this is what we're given. The idea is that the machine state is changing over time as it receives a sequence of inputs from some external world. So it's got a state at time 0, a state at time 1, a state at time 2. We want to know, can this state be interpreted as encoding a Bayesian prior over some hidden variable h in a way that kind of is consistent and makes sense? So we're going to define this notation of an interpretation map, which is a function that maps this state space. The state space of the machine was called M. This roughly corresponds to theta from before. The state space of the machine is called M. So this is going to be a function that maps the state space to probability distributions over some hidden variable. And this is, again, just notation. I'm not really going to explain what the notation means, but it turns out to just be really convenient, even though it's a bit unfamiliar. So we can think of this, though, in the kind of more traditional notation. We might write it as P subscript M of H. So it's a probability distribution over H, but it's kind of indexed by states of the machine. It depends on the machine state. If the machine's in a different state, we have a different probability distribution. And the idea is that the state of the machine, the machine is in a given state at a given time, and that this interpretation map can be applied to those states at each time, and it gives us the machine's kind of beliefs about H at time 1, the machine's beliefs about H at time 2, machine's beliefs about H at time 3, and so on. And then we also have to have a model of, like, remember, this is the starting point before. We had this model, somebody just gave us this model of how the sensor values are going to depend on the hidden variable. Here we have to say, does there exist a model that's going to obey this equation that I'll put up later? So we also have to have this model, which is just a function from hidden variables to probability distributions over sensor values. And now this is the equation, which again, can't really explain the notation. It's just a picture of an equation, I guess. But this is the equation that it has to obey. This is from a paper by Bart Jacobs from last year, 2 years ago, sorry. The agent's current, so what does it say? So this is the equation that tells you that these things form a conjugate prior. It's an equation in terms of 3 functions. So remember, U here was the function, like, don't worry about trying to read the equation, it's just each individual term is a function. So U is the update function for how the state of the machine updates as a function of its input. Psi was the interpretation map that takes the state of the machine and tells us what we think the machine, according to this interpretation, what does the machine believe currently about H? And phi was the model, which is basically saying, what does the machine believe about the next sensor inputs given a particular value of H? And what the equation, when you figure out how to read the equation, what it says is that the agent's current belief about the next sensor value and the hidden state has to be equal to the average of the agent's next belief about the hidden state. So this is kind of this is a crucial property that Bayes' theorem has, that your future beliefs have to be equal to the expectation. Sorry, your current beliefs about the future have to equal the expectation of your future beliefs about the present. Right? That's kind of not very obvious, but really fundamental property that Bayesian reasoning has. And if we were to write that in more traditional notation, it just ends up looking like this, right? It's P of S given H, P of S, the P of S comma H equals P of S times P of H given S. But there's a lot that ends up kind of hidden in this term when you write it this way. It kind of doesn't give you a clear impression of the role played by each of the moving parts in this story, right? The role played by each of these 3 functions. So probably this isn't super clear, but the point is that it makes this picture really concrete. Right, so this picture I gave you in the beginning, you have the physical state of the machine, and that's just changing over time according to dynamical laws. And then along the top, you have the beliefs updating according to Bayes' theorem. And then you have this function given by the green arrows that the map states to beliefs, and this whole thing has to be consistent. So this equation is what that means for that to be consistent. That's what it means for the belief updating to be consistent with the thing. So this green arrow corresponds to psi here, and phi also has to be there. So, so this equation came from this paper by Bart Jacobs. We've extended it, me and Simon and Martin have extended it to Bayesian filtering, which is the case where, so here all the way through I was talking about Bayesian inference, which is what we call the case where the hidden variable doesn't change over time and you just get IID samples. The filtering is the case where the data actually comes from a hidden Markov model, so the hidden variable does change over time. You can write down a very similar looking equation in that case. You can also do it in the case, this was one of Simon's contributions, you can also do it in the case where the machine is stochastic, so it's not updating deterministically. We're working also on extensions to approximate Bayes, which is pretty important if you're into the free energy principle. So all of this was about exact Bayesian inference. And agents that take actions as well as receiving input. So that's also obviously a really crucially important thing. But some results from this analysis, well, one is that some systems really only admit trivial interpretations. So trivial interpretation means one where the prior is always exactly the same as the posterior, no matter what data you get, you never update because the sensor values don't tell you it, don't kind of relate to H at all. They don't tell you anything about it. So if we disallow trivial interpretations, then there are systems that just don't have an interpretation at all. That's usually because they're just too random. Their state updates too randomly to admit an interpretation. One implication of the way that we've approached this is that an interpretation, the way we've defined it, really only depends on the system. It doesn't depend on the environment at all. That's quite a big difference from the free energy principle, where their version of an interpretation depends on the stationary state of the combined agent environment system. But we think that's actually a good thing. And the reason is because something that's doing reasoning might be consistent, like it might have perfectly consistent beliefs about the world, but just be completely wrong. So it might not even live in a world with the same causal structure as its interpretation suggests that it does, right? So you could easily have an agent that believed it was receiving inputs that are conditionally independent given an unchanging hidden variable, but it was actually receiving inputs from a hidden Markov model. There's also a really, really interesting subtlety that comes up. Seems like a trivial point, but I think it's actually kind of deep. That comes up if the agent believes an input is completely impossible, but then receives it anyway. Because if the agent's beliefs are allowed to be wrong, then the agent can it's perfectly consistent to believe that I will never, ever, with absolutely probability 0, never, ever observe a red cat, right? So totally consistent thing to believe. But then if I do see one, how should I update my beliefs? So the consistency equation that I showed you has this property that it kind of has this explosion principle. If I ever observe something I thought was impossible, my posterior can be literally anything at all and it's still consistent. But there's other possible choices, and I think this might lead to a way of formalizing what's called improper priors in Bayesian probability theory. So I think that's actually pretty interesting. So I guess to try and conclude, what I've shown is that you can mathematically formalize this notion of interpretation that's very similar to Dennett's ideas, which kind of links this world of Bayesian inference to the physical world. So there's a lot of work still to be done in understanding. So there's another whole thing I didn't mention, which is that the state spaces that I showed you were kind of just a set, right? But the state space of a brain is divided into individual neurons, and there might be all sorts of things you can say if you felt like trying to interpret a brain about which job each neuron is doing, like not just the whole thing put together, but individual, like how does the whole relate to the parts is what I'm saying. Anyway, there's a whole lot of really interesting work to be done mathematically, but nevertheless, I think this actually represents progress in our understanding of how minds relate to the physical world and ultimately to how the brain functions. It's kind of progress in the kind of formalization of philosophy of understanding how the mind relates to the brain, and I'll end it there. Thank you.
Thank you very much, Nathaniel. We have time for taking some questions from the audience. Lana, please.
Yes, I have a very basic question. I mean, I didn't understand everything, but one thing that is probably very important that I didn't understand is the interpretation map. Is it something that we decide, and it could basically be many different things as long as it satisfies some constraints, or is it something that the agent has and we're trying to find it?
No, it's definitely something that we decide. It's because the point is that as a result of the analysis, there is not one so if an agent has one interpretation, then it also has many others. That's like a kind of unavoidable thing. So it's actually like kind of, I guess part of the point of this is it's sort of wrong to think in terms of the true interpretation of something. And it might exist, right? If I designed a robot and then gave it to you, then there is like a true interpretation in that I had one in my notes when I built the robot, right? But there's no, but that depends on me as well as on the robot. So that's kind of a key point.
I see. Thank you.
Any more questions? Takashi, please.
Hi, that was a nice talk. Thank you very much. I have a very simple question. If everybody is, facing the same, sharing the same environment, and so that, do you think everybody got the same belief, so that there is no individuality or uniqueness emerges? I think we have to explain why there is an emergence of uniqueness or individuality or personality. So if you have any comments on this, please.
Yeah, okay. Yeah, this is a really interesting question. So so if you sort of assume that people are Bayesian reasoners, which I don't know if we should assume that or not, but if you do assume that, then there's this kind of classic result in Bayesian probability theory that says that eventually priors wash out, right? So if you give people enough data, they should always agree on the posterior, assuming that they didn't think things were impossible to start with. But I think but I think that we because we also live in the world and take actions, that means that we don't all get, even if we live in the same environment, we don't always get the same data because we can choose which books to read. So maybe that is part of it. I don't know. I mean, I'm not sure what I presented in the talk can answer the question, but I think it's a really good question.
Okay. Thank you.
Thank you. Can I have one question?
Sure.
It's just I just wonder, like, when you say there's a two different, not rebel, but the Bayesian updating the world and the physical world. Is it still just interpretation? I mean, like there shouldn't be a causal effect from the, Bayesian description to the physical world. I mean, you can still describe everything in a physical basic rebel. So I just wonder, is it like what is actual benefit to describe in Bayesian rebel? I mean,
yeah, I mean, this is also kind of really important mystery, right? So in Dennett's story, which Dennett has the advantage that he's talking about human beings, and it's kind of, I don't know, he's not formalizing things in the same way. The point is that if I tried, so in principle, I can predict your behavior by just using physics, right? In principle, I could do that, but in practice, I can't do that at all. Right, but like I'm talking to you now and I'm kind of predicting, I guess you're going to listen and understand some of what I say, and I can make those predictions because I treat you as an agent. And I couldn't possibly do that practically by treating you as a physical system. So it does give you a lot more, insight into the system, even though, like, in some level, in some way, there is no causal flow back from the interpretation to the physical system. But the point is that doesn't make the interpretation irrelevant or arbitrary.
yeah.
Yeah.
I see. Interesting. Maybe we can take another question if there is. Or otherwise we can move to the next talk. So thank you, Nathaniel, again.
Thanks very much.